I want to talk about the second part of chapter 26. Okay, the first thing is we are going to talk about vision corrections. And this, like one of the most common vision defects, which is the nearsighted, is going to happen when the lens is too strong or the eye is too long. And therefore, the image is going to form somewhere here before the retina. And these objects, when nearsighted, they're gonna be having the inability to see far objects or distant objects, where they are able to see close objects clearly. And I will say the eye is gonna converge the rays like very early. Here we need also to introduce what is called the far point, which is the distance to the furthest object that can be seen clearly for like normal eyes. This is really, I will say, is gonna be the infinity, okay, for for our object, for our eyes. Now the other defect, it is farsighted, and it's like the opposite. We're gonna find that either the eye is too short or the lens is too weak, and therefore the image that is gonna form is gonna be behind the retina, after the retina. And these are really the farsighted. They are unable to see close objects clearly, but they are able to see objects at distance, or like the distant objects good. Now the near point for for a normal person, it is the distance to the closest object that can be seen clearly, and normally that one is for normal people without defects is 25 centimeters. Now, what we need to correct, okay, for correction of nearsighted, we want to, the rays to diverge for a longer distance, and therefore we're gonna use a diverging lens. A divergent lens means it's gonna be the concave one, and therefore we're gonna make the image forming on the retina. Here we have a question: what power of like lens is needed to correct the vision of a nearsighted person whose far point is 30 centimeters? Assume the lens, the corrective lens, is held 1.5 centimeters away from the eye by eyeglasses frames. Okay, then here we have nearsighted. Then right away we need to conclude that it's gonna be a divergent lens. We know that this is really the object here, and therefore this is where the image is gonna form. We know that the distance between the lens and the eye, it is 1.5 centimeter. Therefore, okay, when we're gonna decide on the distance of the image, we know that the lens will produce 30 centimeter from the eye, but the lens is 1.5 centimeter from the eye. Therefore, the distance for the image is going to be negative 28.5 centimeter. Why it is negative? Because it is to the left, and the object is to the left. We're going to say 1 over f equals 1 over di plus 1 over do, and that is that distant object is at infinity, then 1 over infinity plus 1 over di, and that is going to give you a negative 3.51. And that is, of course, reasonable, since it should be a divergent lens, then it should have a negative power. For the far-sighted people, we need to have a convex lens, okay? And here, so that like instead of making it like forming behind the retina. We're gonna have it forming on the retina. This is really the conversion, or we call it double convex. Here again, another example. What power of lens is needed to allow a farsighted person whose near point is 1 meter, okay, to see clearly that is an object that is 25 centimeters away. All right, and the same, it is 1.5. Okay, the diagram is very helpful. Again, the object is here. This is the object, which is at 25 from the eye, and the lens is 1.5 from the eye, and the image is forming somewhere here at 1 meter from the eye. We need to find what's the distance of the object. It is 25 minus the 1.5, and the DI is going to be the 1 meter minus the 1.5. I will plug in these numbers. 1 over F, which is power equals 1 over DO plus 1 over DI. And this is really giving us a positive number, which, means that this is really a convex lens. Colors. Now, the theory of colors is telling us or making us predicting what is going to be the color of the thing. Now, opaque things, opaque means the ones that light cannot go through. I can see the opaque blue because it will absorb all the colors and reflects blue only. Okay, then here, if you look at the blue object, it has all the colors. White light has all the colors. They're gonna hit the blue, but the only one that is gonna reflect is the blue. If it is red, appears red because only the red is gonna be reflecting. White reflect all the lights. Okay, then I will have all the colors, and then it will reflect all, whereas the black is gonna absorb all, and there is no color that is really reflected. If I have something that is transparent blue, then I will say that object is going to absorb all the colors and makes the blue go through. Okay, and the rods and cones are really the things, the cells that they are really responsible for colors in our eyes. Now, microscopes and telescopes are really working with double systems or composite systems, where we have two lenses. One of them we call it, let's say for microscope, one of them we call it the eyepiece, and the other one we call it the objective lens. Okay, here I did draw this. Okay, and then this first one, this is first the object one. It is standing in front of the first. This is lens. I will call this lens one in the the order of the forming the images. Okay, therefore the one light is gonna parallel to the optical axis, is gonna go through the focal point, and the second one is gonna through the center. Therefore, this is my first image. Now, my first image is gonna be the object for my second lens, and therefore this is one light, and then it's gonna refract through the focal point for the second one, and the second light, the green one, is gonna go through the center, and then finally they are going to form the image two. The magnification, the overall magnification, it is M1 times M2. Let's talk about how this is Calculate the magnification of an object placed 6.2 millimeters from a compound microscope that has 6.00 millimeter focal length, objective, and 50.0 millimeter focal length eyepiece. The objective and eyepiece are separated by 23 centimeter. Always, it's good to have a diagram, and that is the diagram here. This is the first lens. This is the object here. This is the object, this is the first lens, and this is the second object. We know that the distance between the two lenses is 23. Now, what I will do, I will work first on the image formed by the first lens, and I know that my D object is 6 millimeters. 6.2, yeah, and F1 is 6 and 50, all on millimeters. Then I need maybe to just convert the, the 23 centimeter here, all right, which is going to be 230 millimeters. Here I will say 1 over D object di equals 1 over f1, and therefore I will be able to calculate what is really going to be the distance of the image, the first one. It is 186 from the first lens. Therefore, on the diagram, this is the image, and it is at 186 millimeters from the first lens. Now, for the second one, I want to find what is the object. I'm gonna give it a prime, and I know that it's gonna be 230, the distance of the object, minus 186, and that is gonna give you 44 millimeters. And then here the object prime, di prime equals 1 over f2, and from that I will be able to find 1 di prime as 1 over f2 minus 1 object prime, and from that I will be able to say that di prime is gonna be negative 36 centimeters, and that is gonna be from what? From the second, what is called second lens. Okay, I can calculate the first magnification, M1, as negative 30, which is gonna be di over do, and that one di prime over do prime. When I multiply, I'm gonna get negative 250, and that is gonna make, the image, I will say, enlarged. It is it is upside down because it is negative. Okay, telescopes are the same idea. They are used to view distant objects, producing an image that is larger than the image that can be seen by the unaided eyes. You know that most common types used two convex lenses as shown, all right, and the same idea as the microscopes. The only difference is that the object is very far away from the telescope, and therefore the distance of the object is infinity. And here I will say O stands for object, of course, and E stands for the eyepiece. If we look at this here, we're gonna find that DI will form the distance for the image is gonna form what is really the focal point of the objective. We have for telescopes, we measure angular magnification, which is minus the focal of the objective divided by the focal of the eyepiece. And telescopes can be also made with concave mirrors, as its first element or objective here. For example, like these, where is gonna be the light that is coming from far is gonna hit the mirror and then gonna hit another mirror that is really flat and then go through the eyepiece. Now the last thing we're gonna talk about is aberrations, which is kind of defects in lenses. And the first one, we call it the color or the chromatic aberration, and that is really caused by the dependence of the lens index of refraction on the color of the light. And the lens are really more powerful for violet than for red, and they're gonna have that instead of having that form as one single dot, is gonna diverge and is gonna cause a spectrum because of that defect. There is also something called coma, which is an aberration caused by an object that is off center, and that is often resulting in that shape that is really gonna make the light refracted is gonna be it has a deformation. Also, we have the spherical aberration that is caused by rays focusing at different distances from the lens. All these, they're gonna make more limitations on using lenses in telescopes. Okay, like the most powerful telescopes, they are made up of they use mirrors. When it is come to designing very large lenses, it's hard. Thank you and have a great day.